Consider this following somewhat entertaining example where we will be having an application, an example. We'll go over this example to practice our alpha and beta skills. So here we go. Suppose that we wish to test the null hypothesis, H0, that the proportion P of ledger sheets with errors in them is equal to 0.05. This is the probability. Or lower, I guess, versus the alternative that the proportion is actually larger than 0.05. So let's type this. So the null hypothesis is that the probability that we will have an error is 0.05 at the max, versus the alternative hypothesis is that no sir, this is, we want to reject that and we think that it is really greater than 0.05. Now, in order to do that, obviously we need a statistic, a test statistics, and then a rejection region. So let's talk about this. So we design the following scheme, which will end up being our test statistic. Two ledgers are randomly selected, and if both are error-free, we reject the null hypothesis. All right, if both of them don't have any errors in them, we reject the null hypothesis. If one or more of them contains an error, we look at a third sheet, which is kind of like, it will be the decider. If the third sheet is error-free, we reject the null hypothesis. Again, in all other cases, we just accept the null hypothesis. When we say in all other cases, if well, you guys see this algorithm. So basically, if when you look at the first two ledger sheets and they contain at least one error, then we go to the third sheet. So if the third sheet comes out to have an error, then we accept the null hypothesis. So when I first read this example, this question, I was like, what? Seriously? Because remember, the null hypothesis is that P is a small number, right? So if that's the null hypothesis, then how come our rejection region will be such that like no errors will be a cause for rejecting the null hypothesis? Does that make sense? So technically, we should have done something like this. We should have done like, we randomly pick two ledgers, and if one or two, if none of them is containing an error, then it means it is in support of the null hypothesis, right? Because the null hypothesis claims that the probability of error is small. And now look at this test. I mean, this is really messed up. So let's start with the first problem. What is the type 1 error based on this language? Well, type 1 error is the probability of rejecting the null hypothesis while in fact it is true. In this example, yeah, it is saying that the proportion of ledger sheets is more than the ledger sheets which are in error is more than 0.05. Whereas in reality, it was actually less than 0.05, right? So yeah, so that's what is meant by A. So if you want to interpret it for this situation, it is saying that concluding, let's say concluding that P is greater than 0.05, while in reality it was indeed less than or equal to 0.05. So what is the value of the alpha associated with this test? Now, so the alpha, remember, alpha is just the probability of rejecting H0 while in fact it was true, while in fact true. So such a probability, so will be equal to, well, so it will be equal to one of these situations. Either the first two are both not in error. So I use the letter N as not error. versus E, capital E, I will use it for error. Either both of the first and the second came out as no error, the two samples. In that case, we reject the null hypothesis. Well, in fact, it was true, so we will, given that it was true, or we might as well reject the null hypothesis by, if the first two are like N and E, and then the decider, the third one, is again N, or it could be the probability that it was E, the first one error, the second one no error, and the third one error, or it could be the first two have errors in them and the third one has no error in them. Now let's calculate these probabilities given that in fact the null hypothesis was true. So the first one is, if in fact the null hypothesis is true, the probability of having an error is 0.05. So the probability of having no errors is 0.95, and we need to square it because we have two no errors. No error, error, no error. So it is in fact these three situations are symmetric. The only thing which is changing is the ordering, so it's really 3 times. I don't have to recalculate it 3 times in a row. Does that make sense? All right, so the probability of no error is 0.95, and we have 2 of them, right? Oh, actually it's not, sorry for that. This one has 2 E's in them. Sorry for that. Okay, so this is really 2 of them. So the second, so this one, these 2 are the same. So 2 times. So the no error is 0.95 chance square, because 2 times no error, and 1 time there will be an error, which is 0.05. And then for the last one we have 0.05. There's a chance of error, 2 errors in a row, and then 1 no error. There you go. That's it. So if you add up all these numbers, you will get an outrageous alpha of 9. Oops, how did I manage to do that? Okay, hold on. We will get, oops, okay, there you go. 99.51%. The alpha will be like, there's a 99% chance of making a type 1 error. Well, no wonder, because the test was a horrible test, right? Terrible, horrible test. We can design a way better test than that, well, down the road, I guess. So for part C, in terms of this problem, what is a type 2 error? Remember, type 2 error is associated with rejecting the alternative hypothesis while it was actually true, right? So in this example, it is like you are concluding that the probability of an error is 0.05 or less, while in fact it is greater than 0.05. So in that case, you commit a type 2 error. And finally, how do you measure the beta, the type 2 error in this case, in terms of a function as a p, where p we can, or PA, let's call it P alternative, or P true if you want. So if the alternative was true, and you just rejected it, you rejected the null hypothesis, then what could have been the scenarios? There are one of these 3 cases. So let's do it here. So it means beta is equal to, so probability we reject, oops, probability that we reject the alternative hypothesis while in fact it is true, while HA is true actually. So that would be one of these 3 cases. Either we have an error, all 3 of the sheets are in error. The first 2 are definitely has got to be in error, right? Well, actually no. The first 2 are in error, and then the third one is in error. The first one is not error, the second one is an error, and the third one is not an error, I think. Yes. And then what else could it be? The first one is not error, or error. The second one is not error, and the third one is error. I think that's pretty much it. These are the only 3 cases that can show up, and these 2 are symmetrical, so we can just, when we calculate it, we will multiply it by 2. So the probability of this happening is just whatever is the probability of the alternative. So we decided to call it PA. So this will be really PA cubed plus 2 times, the PA, 1, 2 observations like that, and then 1 minus PA, multiplying it with 1 minus PA. Just to clarify this, so suppose that the alternative is that the alternative claims that PA is really, so remember the alternative is more than 0.05, so suppose it's 0.1. So what we can do is we can just plug it in. So 0.1 cubed plus 2 times 0.1 square times 1 minus 0.1, which is, let me try to see if I can calculate it, 0.001 plus 2 times 0.01 square is 0.01, 2 times that is 0.02, and I need to further multiply this with 0.9, which is going to be, so the first number remains, plus the second number is going to be 0.0018, I think, if I'm not mistaken. So they will add up to 0.0019. So that will be our beta calculation. But obviously there's a big, huge gap between them. And besides, alpha is so big. Remember, most of the time our main concern is alpha. We don't want to commit a type 1 error. And look at the alpha here. 99% chance we'll commit a type 1 error, meaning we will reject the null hypothesis in favor of the alternative hypothesis, while in fact the null hypothesis is true. This is definitely not acceptable. So a better one would have been to the opposite, right? So instead, when you pick 2 ledgers, you randomly select them. If both of them are error-free, no errors in them, then you will maintain the null hypothesis. And then everything else, let's say that we don't want to worry about the third one. So anytime if both of them are error-free, we maintain the null hypothesis. But if one of the 2 are in error, then we reject the null hypothesis. So then, for instance, let's consider that algorithm. Then this will be significantly an improvement on what we did so far, right? Let me actually quickly show you that. So the new test, oops, what did I do here? The new test statistic, the test, and the rejection region are the following. So our new algorithm says draw 2 ledger sheets, draw 2 random ledger sheets, and if no error, maintain H0. If at least one error or both error, right, then reject H0. I think this will turn out to be infinitely better. So for instance, let me remind you of the null hypothesis and the alternative. The null was that this is 0.05, and the alternative claims that there is more. So we make more defective ledger sheets, or errors, sorry. There are errors in our ledger sheets. All right, so with this new algorithm, so what we will do is alpha, which is the probability of a type 1 error, is going to be equal to, well, it's going to be equal to committing a type, or let's do it one more time. It's saying that we reject the null while in fact it is true, while H0 is actually true. So the only way we will reject the null hypothesis is if at least one of them is in error, right? So the probability that either we have the first one is in error, the second one is good, or the first one is good, no error, but the second one has an error, or both of them has errors. In that case, in those cases, we will reject the null hypothesis while in fact it is true. And so let's calculate the probabilities of these happening. So the first one is an error showing up is 0.05, so that was the 0.05 times no error is 0.95, plus, again, actually this is symmetric, so I can, well, okay, let's just do it in 2 steps, I guess. 0.05, and then finally the probability of both of them showing an error is 0.05 times 0.05. All right, so let me make sure I'm not messing up anything here. Yes. Yeah, so okay, so if you just multiply these out, I'm pretty sure we will get some really small value for alpha. You know what? I'm gonna use my Excel now. At this step, let's just go ahead and calculate it here, these numbers. So the first number is equal to 0.05 times 0.95. The first term is that number. The second term is 0.95 times 0.05, that's the second one, and finally the third one is equal to 0. This one is very negligible, times, oops, sorry for that, 0.05 times 0.05, and boom. So our goal is so therefore the alpha oops, come on, is equal to, it's equal to this number plus that number plus that number. And now suddenly look at the alpha. It is about 10%, which is really reasonable. So the way we interpret, like the test and the rejection region was wrong, right? It was wrongly set up. The rejection region shouldn't be rejected if no error. It should be really maintain it if no error, like rejected if you see at least 1 or 2 errors, because H0, the null hypothesis says that the probability of error is small. If it is small, when you take a sample and you don't see any error, that should be evidence that there is no errors, like the error in the ledger sheets is a small probability. Does that make sense? And that's it. So this is the alpha. In a similar way, you can quickly calculate the beta as well. Okay, let me try to write it here. So the probability of a type 2 error, which is basically the probability that you will be rejecting the alternative hypothesis while in fact it is true, while true. Well, this is the only way you will reject the alternative hypothesis. Let me see, how did we do it? So we will maintain the original. So we will reject an alternative hypothesis only when there is no error, right? So therefore, and that's exactly the opposite of what we did earlier. So if there is no error, no, then that's the probability that we want. So probability of no, given that HA is true, right? And the true HA, we decided to go with this, like 0.10 for instance. So therefore this will be like no would be a 0.90, and then this one is no error again is a 0.90, right? So that's like 0.81 or 81%. So the beta is kind of not as good as, oops, how did I mess up this? Okay, not as good as the alpha. Alpha came out as a 10% versus here the beta comes out as 81%. So probably like we did in the previous cases, we can improve our test by sampling more stuff. Just 2 ledgers randomly picked is not a good test. So maybe we should look at a random sample of maybe 10 different ledger sheets, and then we can have a better alpha and then better beta. But in all these occasions, so what we want is when we pull those ledger sheets, the test statistics and the rejection region should be such that we should only reject, so we should maintain the null hypothesis if less number of sheets are in error, and only reject the null hypothesis if the larger number of sheets are in error, right? So we need to make sure we set up the test and the rejection region in a correct way. So hope this was useful, and looking forward to see you guys in our next video.